Hi, I'm Maria from the Ready Set Grow team, and I'm going to be explaining to you my camera system. So why build a camera system? Because it could monitor the health of the fish and on the plants. It also demonstrates 3D printing, relays, sensors, Arduinos, motors, gearboxes, electronics, and more. But really, it's all because I just love photography. First, I'd really like to thank our sponsor, IGUS. They make great linear rails, bearings, and energy chains. This linear rail helps the camera slide smoothly and accurately, and what makes the IGUS rail really neat is that it doesn't need grease or oil for lubrication, ever. This part is the slewing ring and makes it easy to rotate the camera. The hole in the center is great for connecting the wires. Finally, something you'll see on lots of machines is the energy chain. This keeps our wires neat and tidy on a moving system. We are now extending the wires for the stepper motor. Now we have a long cable to go into the energy chain. Now that I explained the part of my system, let me show you what it can do. What parts are needed to do this? You already saw all the cool IGUS parts. These provide the ability to move, but not the force to move. The force needs to come from the motors. There are a few special parts like these 3D printed parts. Let me show you how I made them. Last year, I learned some very basic SolidWorks skills for our cookie frosting machine. I learned a little more this year. Basically, my parts are not too difficult, just extruded shapes with holes. They call this 2.5 dimensional because it's easy to make. We started off with a block the size of the material we would make it out of. Then cut a hole for the IGUS bearing. Then cut it to thickness. Then made a surface for the bearing flange to mount. Put in the pattern for the stepper motor to mount. Stretched out the opening so we could tighten the belt. Routed the quarters to make it look pretty. And finally added some holes to bolt it to the IGUS carriage. We've needed to save it in a generic format called STEP so that we could bring it to Fusion 360. Here's my part in Fusion 360. To run the toolpaths, we need to select CAM, or Computer Aided Manufacturing. We first need a setup. It shows us where our stock is, so basically the block of wood that we started with. It also has an origin in the corner to show us where the machine's 000 point is. Then we generate the toolpaths. We want to cut a pocket. We pick a tool. We use a 1/4 inch router bit. We pick the geometry and pick OK. It generates the toolpath. We want to cut the outside edge. That is a contour. We use the same tool. We picked up the geometry off the outside edge and hit OK, and there is the toolpath. Suppose you want to see what this looks like. We just hit simulate, then hit the play button. It shows how the cutter works. it cuts the pocket and the outside edge. That is cool. The final thing is that we need to generate the G-code for the mill to cut it out. We use Fusion 360 for a lot of our parts. Our boards for the mounting the Arduinos and electronics, the plant holders for our grow bed, Shreya's pH readout device, and I really wanted to work for the base for my camera. Here's the base being milled. I was so excited. Here it is cutting the top surface to thickness. Now it is cutting the mounting surfaces and the attachment holes. Unfortunately, when we assembled the motor, it was not strong enough to turn the belt. Redesigned the platform for a bigger motor and 3D printed the one you see on the final device. Here is a spare sprocket that we printed. Here you see the platform and other parts that are mounted on the camera system. We then put a GT2 belt over the gears, and that is how the camera rotates. GT2 belt and sprockets are pretty cheap but work really well. You can find them on most 3D printers, including the one here at Smart Labs. So how did we turn the sprocket? We used a stepper motor and a gearbox. Stepper motors are great because they position very accurately. They move in single steps. Let me show you a quick section from a video from YouTube to see how it works. I'll put the link in the description below.
It has a different number of teeth than the rotor, 4 in this case. This is done intentionally so that only one pair of rotor teeth is aligned with the stator at a time. You can explain how this stepper motor works by yourself. If you de-energize coil A and energize B, it becomes clear that the rotor will rotate as shown.
That showed how the motor turns one step. Just put lots together and it can move forwards and backwards. Please review more videos to understand all about how it works. The stepper motors are driven by this motor driver board from Adafruit that runs off the I2C lines. It is a master-slave system, and you can connect lots of devices to the same 2 lines. All you really need to know is that you must connect these 2 pins on the Arduino to these 2 pins on the driver. They are the clock and the data lines for the I2C. We also needed a power supply to supply enough current for the motors. How did we get linear motion? Basically the same strategy, except we attached the belt to the IGUS cart and just turn the sprocket to make it move. My code video will show you how to turn the motors. A critical function is homing. This is when a machine learns where it is. To do this, we move the cart until it hits a switch called a limit switch. And then we rotate the camera until it hits another limit switch. We then call this the home position in the software. You may be wondering how we focus and take a photo. Well, we studied this remote, and when you press partially down, it focuses. And when you press completely down, it takes a photo. To get a better understanding of this, we have to take it apart. As you can see here, when I press the top 2 together, they focus. And when I press all 3 down, it takes a photo. This is a perfect application of a relay. The big yellow demo button is used for starting the system. That is just to read on a digital input pin, and the light goes on based on a digital output pin. If you look under the button, there's a little micro switch. When you press the button, the switch is pressed. See all those soldered connections? I soldered those. Now the final trick in my system is to get continuous time lapse without jumping at night. We need to only take pictures during the day. To do this, I use an analog light sensor and a potentiometer so I could adjust the sensitivity. If it sensed enough light, it would take a picture, and if there wasn't enough light, it would wait. We're doing a 3-week time lapse to be ready for the RoboFest World Championship, so hopefully it works. Please come see our system at Lawrence Tech on May 19th. Thanks for watching!